Oops. I'm sitting here trying to close windows and things are just playing on their own here. So I I apologize for the random Life of the Lavish that popped up there. Please don't copyright strike me. Hi, welcome to Chem 163. Today's kind of a weird day because, as you probably all got the email or text or whatever, there was some event that occurred on campus that resulted in a lockdown. I unfortunately don't have any more information, and I've been told to direct you to the EVCC website. Um, that is all the information that I personally have too. I'm not going to spend the lecture talking about the lockdown because I don't know anything about it, so we're just going to do our lecture. Oops, now I'm hitting buttons on my keyboard that shouldn't be hit, and something just popped up. My understanding is that everyone is either on campus has been directed to go home, and that the campus is closed, and that's really all I guess I can say at this point, because that's all I have. So I hope everybody is okay. As far as administrative stuff, I put it on the bottom of the screen. The last call for Chapter 14's quiz is tonight. If you turned that quiz in already, I am going to give you the extra credit points that I mentioned in the announcement for doing it before the exam. If you turned it in later than that, then it's due tonight. You could still get regular credit for it, so that's fine. And then the other important thing to mention is that this week we're going to do lab number 4, which is buffers. We're going to skip lab number 3 for now. I'm going to ask if the NMR is working, and if it is working, we'll do lab 3 next week. And I will make an announcement on that later. Yeah, that's where we're at. Finally, regarding exams, that was the other thing I wanted to mention. I have graded all the exams. I will be posting scores for all exams tonight. I don't want to talk about exams publicly on the channel because, I mean, there's not really much to say other than they're done and graded. And if you have questions, you can always ask me. I will return those to you in person on Friday, but your scores will be posted on Canvas tonight. So we'll do that later. I don't know why my cats are jumping up and down next to me. All right, there we go. Sorry, I had cough there. All right, so we're going to go finish up buffers today. So last week we talked about how to calculate the pH of a buffer, and we used this equation, right? Well, I don't need to write it down. I could just throw it on the screen here. Where is my Henderson-Hasselbalch? There it is. So we use this equation. pH equals pKa plus log of base over acid. And you can do that for any ratio of acid to base as long as the x is small approach is valid. It turns out that the range in which the x is small approach is valid is plus or minus a factor of 10 or so. What that means is that the base or the acid can be roughly 10 times more concentrated, because if I had 10 times more concentrated acid, it would be 1 divided by 10, which is 0.10. So if you compute this ratio, base over acid, and you get a number between 0.1 and 10, then the x is small approach will be valid. Now, depending on how concentrated your acids are, and how much stuff you put in there to react with it, you will get a different result in terms of the concentration of your base to acid being within that range. So what I mean is that if I use 0.01 moles of like additive, so here I'm adding hydroxide to a weak acid component of a buffer. If I initially had 0.1 moles in there versus if I initially had more of it but very little of the other thing. Sorry, this is the one I should be looking at. Then the effect ends up being much more pronounced on this one because there's so little of this. Here, they're both roughly equal. So the closer your base and your acid are to each other in terms of concentration, before you add anything in there, the more effective the buffer will be. As things get further and further apart, what ends up happening is that you end up running out of one component, and then when you do the calculation for the Henderson-Hasselbalch, the X is small approach doesn't succeed anymore. You can see here that doing all of the math through here, the percent change in pH is about 1.8 when my buffer components are equal, but it's about 5% when they are very, very far apart. In fact, they are barely within the 10-to-1 ratio. So what we're going to want to do is we're going to want to keep our components roughly equal in order for the buffer to be effective. Otherwise, we end up outside of the range, and it's hard to calculate the pH of it accurately because our equation doesn't model what's actually going on very well. Now, the other feature that we can use here is just concentration. So if I just straight up have a more concentrated buffer, so here I have 0.5 versus 0.05, and in both cases I'm going to add 0.01 hydroxide to it. 0.5 minus 0.01 would be 0.49, but 0.05 minus 0.01 would be 0.4. Here I'm changing by about 20% difference. Here I'm barely changing it at all. So since this one barely changes, the pH barely changes as a result. But if I consume most of my buffer, the pH ends up changing by more. So more concentrated buffers are more resistant to pH changes. And that's sort of a well, duh sort of circumstance, because if you're adding acid or strong acid or strong base to your buffer, you're consuming the opposite component of it, right? So if I had strong acid, you'd be using up the weak base part of the buffer. And if there's less of it to use up, then yeah, the pH is going to change more quickly. All right. Now, a buffer is only effective within a given pH range. What that means is that if I want to have a buffer around pH, say 4, I cannot use any conjugate acid or base. It's going to depend on the pKa of the acid in the buffer. So, for instance, the pKa of acetic acid is, I want to say it's like 4.7 or something. Let me look this up, actually. pKa vinegar. 4.75. Yeah, there we go. Now, if we look at the Henderson-Hasselbalch equation for this, we can make a very interesting sort of mathematical analysis that shows us that you can only operate in certain ranges here, right? So if I have my base over acid, let's do this in one color here. Let's suppose that I have this. So this would be the base is more concentrated by a factor of 10. I punch this in the calculator. What is the log base 10 of 10? Well, it's just 1, right? So what that means is that I would get 4.75 plus 1. So the maximum I could do of this would be pH 5.75. If I had gone to the extreme and had my base be 10 times more concentrated than my acid. We could do this instead. We could say that, okay, base over acid equals 0.1 molar over 1 molar, which would equal 0.1, and then log base 10 of 0.1 is negative 1, right? Hopefully everybody remembers how logs work. So that means my pH would be pKa 4.75 minus 1 or 3.75. So this would be my effective range. Or in other words, pKa plus or minus 1. So if I wanted to make a buffer out of acetic acid, I could only ever possibly get pHs between 3.75 and 5.75. Because if I went past that, it's no longer a buffer, right? I've consumed too much of one quantity of the buffer for it to be an effective buffer. But anything within that range would be eligible. If I wanted a buffer around a different pH, like say pH 6.5 or something, I cannot use vinegar to do it. So when you are asked to construct a buffer, which is kind of what the whole point of this first half hour is today, your task is going to be to select the appropriate buffer. And the first thing you want to do is you want to pick the pKa closest to the buffer range that you want. If you want to make a buffer around pH 8, pick the buffer components that have a pKa that is closest to 8. It can be within plus or minus 1 of the pKa, so 8 has to fall within that range. A 7.2 pKa is acceptable because 8 is within 1 of 7.2. But a pKa of 3 would not be. So that's going to be our objective here. There's our range. Lowest pH, pKa minus 1. Highest pH, pKa plus 1. And again, that just shakes out of the log equation of the effective range, maximums and minimums for the amounts of our buffer that we can have in the solution. All right, so on the screen here, very easy problem. I want to make a buffer with pH 8. Which weak acid paired with the sodium salt, so basically take the H off and put a sodium, which would be the appropriate buffer? So something obvious thing, it would be the hypochlorous acid, right? Because it's the only one that's even close to pH 8. Like these are way down here too acidic. So none of those would work. So I would make a hypochlorous acid buffer, which of course requires the sodium hypochlorite conjugate base. All right, so yeah, we know which one to pick, but like, how do we get a pH 8 buffer? So we'd have to mix some ratio of base to acid in order to make the appropriate buffer. Well, turns out that that's not difficult for us to calculate, so let's actually do that. Oh, first we're going to pick a pH 4.6. So if we go back here, which one will do 4.6? Well, this is the only one that's close enough. Where'd my cursor go? There it is. So we can use formic acid. I guess we're going to work with the formic acid buffer here. Okay, so we're going to use formic acid, which is HCHO2. And we're going to use sodium formate, which is this one, nacho2. Do not eat sodium formate. Ironically, sodium citrate, which also has the formula nacho, that's the one you want to eat. You actually use that for making nachos. Sometimes chemistry is funny. All right. I need to make a buffer with pH 4.6, and I have this to use. And what was its pKa? Let's go look that up again. 3.74. Oops. All right. Let's make this buffer, or at least describe sort of how to do it. I need to go over here. That's what I want. There we go. Okay. So I want to have... I don't have the pen selected. There we go. I want this target pH. There are the components of my buffer, and the pKa of the weak acid is 3.74. So what that means is that when I solve the Henderson-Hasselbalch equation, I know what this number is, and I know what this number is. So I can then plug those in here. So let's do that and see what happens here. So I want pH 4.60, and that's going to equal the pKa plus the log of base over acid, which I'll then subtract 3.74 from both sides. Oops, my fingers are on the wrong buttons. 4.60 minus 3.74 is 0.86. So I get this, and then I can undo the log on both sides by just doing 10 to the power of, right? So 10 to the 0.86 equals the ratio of base over acid. And when I do that and hit this button on the calculator, 10 to the x, I get 7.24 as my answer. Actually, I think I only get 7.2 because I'm working with logs here. There are only 2 decimal places. And so what this means is that the ratio of base to acid is 7.2. Or in other words, the base is 7.2 times more concentrated than the acid. So, for example, if I had this, for example, if I had 0.72 molar sodium formate and 0.10 molar formic acid, then I would have a pH of 4.60. Because I would then get 7.2 for my ratio. And when I do pH equals pKa plus log of base over acid, which we would get this as our ratio in that parentheses. So log of that, you get pH 4.60. So that would be our ratio. That's what we need to calculate. Now, it looks like on my slide here, I have a few more sig figs. Don't worry about the sig figs for logs and 10 to the powers of. We're not super invested in that right now. Now, if you know what the molarity of your solutions need to be, then you know how to calculate it. Because we've done everything we need to with molarity, right? It's just going to be some application of M1V1 equals M2V2, and having them both be the same concentration for whatever given volume you have. In fact, for one of the labs, you're going to do that this week. That's, sorry, for lab number 4, part of the experiment, what you're going to do is you're going to prepare a buffer with a pH that I'm going to assign you. I'm going to go around with a giant deck of poker cards, and you're going to draw a pH, and then if you get like a 9, I'm going to laugh. Everybody laughs at you because 9 is the hardest. 9 or 10 are difficult because the ammonia buffers aren't great. But the other ones work pretty well. All right. So what I want you to do is I want you to tell me, how do you make a buffer with pH 2.30. So let's go throw this on the screen real quick. So remember, 2.30 is what you want. We'll just right here. So write down which acid you're going to use. Do it really quick, because it's gone. Boop, there we go. Okay. And then what I want you to do is, suppose that you have 500 milliliters of a 0.1 molar solution of the acid. Tell me how much of this corresponding sodium salt of the conjugate base, which, here we'll just tell you what, this is the acid that we're supposed to pick. How much of the sodium salt of that for your buffer do you need to make this buffer? And then assume that when you add your solid into your buffer, it doesn't change its volume. It's still going to be 500.0 milliliters, so that you can calculate its molarity. I'm going to give you like 5 or 6 minutes to try this. We'll go over the answers in just a bit. One more minute, we'll go over the answer. Alright, so let's figure out what mass we need while my cat sits here and yowls his head off at me. Because cat. Oops, sorry, I didn't mean to pick that. Alright, so we want a pH 2.3, and we want to make 500 milliliters of this buffer. Where did I put the pen? Where did it go? There it is, next to the phone. Okay. So, target pH is 2.30, and we've got HClO2, which is our acid, and that would mean that we would use sodium chlorite as our base. And I've already forgotten what the pKa of it was, so I'm going to go back and look. Like 1 point something. 1.95, okay. So let's write that down. All right, so there's our information. So pH equals pKa plus log base 10 of base over acid. And so I know that the pH is going to be 2.30, and the pKa will be 1.95. So I'm just going to subtract them. 2.30 minus 1.95 is 0.35. And that would equal log of base over acid. So then we will just take 10 to the power of that. And that's going to be 2.238. So with 2 sig figs, I'll just do 2.2. Now, I actually know the concentration of the acid, right? So if I multiply it by this number, I'll get the concentration of the base. So the concentration of base would be 2.2 times that of the acid, which would be 0.10 molar, which is just this. And I know what volume I have of that, right? So I could say there's my molarity. That's what this M means. And I have half a liter of this. And we'll just turn it from moles into grams. And we'll go to Lentech. Hopefully everybody remembers what Lentech is. It's just what I go to calculate molar masses. I got 90.44 grams per mole. And so the concentration I would get would be 0.22 times 0.5 times 90.44. So that would be the amount of sodium salt that I would need. So if I was writing a procedure to make this buffer, I would add 9.9 grams NaClO2 to 500 milliliters of 0.10 molar HClO2 and mix well to get a pH 2.30 buffer. And then if you've taken a class from me before, you know the last step of mixing any solution or whatever is always enjoy. All right, so that's how you'd make a buffer. Just in case you know you have to do that on, say, Friday. Hey, you will have to make it on Friday. We're going to throw one other gimmick, though, at you. That instead of adding a solid component, what you would end up adding are two liquid components. And you have to mix them together in the correct volumes. And the lab walks you how to do that. It shows you the algebra. The algebra is a little bit rigorous, I guess we'll say, because you're solving for a variable that shows up in multiple places. Hey, you have Wolfram Alpha. Use Wolfram Alpha. It will tell you what to do. All right. Now, the last term we're going to use when talking about buffers here is called buffer capacity. The buffer capacity is the maximum amount of acid or base that you can add to a buffer before its pH changes by more than 1 in either direction. Now, the more concentrated your buffer is, the higher the buffer capacity. As a consequence of this, if I want my buffer to remain in the buffer region, I need my ratio to stay between 0.1 and 10. The midpoint of that would be if the ratio of the acid and the base was the same, or 1 to 1, or if the concentrations were the same, I should say. The closer those concentrations are to each other, the higher the buffer capacity is. So, for example, if I have these components in my buffer, I made a buffer out of HCN and NaCN. Here's how much HCN I have, 0.010 moles. I'm sorry, 0.10 moles. And then I have 0.050 moles sodium cyanide. Which of these will ruin the buffer? So let's actually draw this all out. I gotta erase all of this work that we just did. Sorry, just a second. There we go. And let's see here. So I have 0.10 moles. This is my buffer. And so what we're going to do is we're going to add HCl. Okay. What does HCl do? It would react with this one, right? So that means that I would react this many moles. And in doing that, I would create the same amount of the other side. So this would be my concentrations at the end. All right. Do I have a buffer after I have done this? Well, obviously I don't, because there's none of this left. I have a weak acid at this point, right? So I no longer have a buffer. So this ruins the buffer. And the reason that it destroys the buffer is because I consumed all of one component. All right, let's look at the next one. You'll notice that look at that. That was clever of me. I made a new layer. Let's add Not 0.5. That would ruin everything forever. I'm going to add sodium hydroxide. Which component does sodium hydroxide react with? Hey, it's this one. So I'm going to use this much up and turn it into the other component because that's how buffers work, right? Oops, that's not how sig figs work, though. There we go. There we go. So adding 0.050 moles of sodium hydroxide would change my concentrations of components like this. But I still have a bunch of each, right? If anything, all I've done is just flip the ratio of the buffer around. Now I have slightly more base than acid as opposed to the other way around. So I did not destroy the buffer by doing this. Oops. There we go. And then finally, if I add this, well, I'm just literally going to do this to it, right? And then this stays the same. If anything, this makes the buffer better. So this does not ruin the buffer either. So the action that resulted in us depleting the buffer was this one. So if you deplete a component of the buffer is ruined. It is no longer a buffer and will not behave like a buffer. That's going to be relevant in the next section that we're going to talk about in just a little bit. Oh, we're going to talk about that now. Look at this. Hey, we made it to the end of chapter 14. Fucking finally, right? All right. This last section of chapter 14 is going to encompass literally everything we've done in chapter 14. So it's kind of like the perfect review to the chapter. So real crucial that you do the practice problems from this section because it will summarize basically everything. All right, we're going to play a game, and that game is called What's in the Beaker? The whole point of a titration is for you to add one component to another in a controlled and a precise amount. However, a lot of the time in Chem 161 and Chem 162, we sort of just give you the components and say, here you go, do the titration, and then tell me when it's done. And you rely on an indicator. The indicator just changes color, and then you know, oh, okay, it's done. I've used up all the thing. And then you do your calculations and everyone's happy. Now what we're going to do is we're going to not use an indicator. We're going to just use a pH probe. And the pH probe is going to tell us a lot of information about our acid and base as they're reacting with each other in various ratios. We're going to see how that influences the pH. All right, so we're going to react an acid with a base until one of them has completely consumed the other. This is going to be called the equivalence point. The equivalence point is the point where you have added the same number of moles of acid to the same number of moles of base, or vice versa. So if I had a 1 molar solution of sodium hydroxide, and I had 10 milliliters of it, and I titrated it with a 1 molar solution of hydrochloric acid, it would take 10 milliliters of that too. If I added 10 mils, I would reach the equivalence point, because there's an equivalent amount of moles of acid and base. Everything is neutralized. Now, you may also hear this called the end point, because this is the end of the titration. What it is not it is not called the midpoint. We're going to talk about the midpoint later. That's something different. What we're going to do is we're going to create a curve. I don't know if this actually has a demo curve here that I can just show you. Yeah, something like this. We're going to make a pH curve just like this. What we're going to do is on the x-axis, we're going to put the volume of sodium hydroxide. If we're titrating an acid with sodium hydroxide. And then we're going to plot the pH on the y-axis. And what we're going to notice is that the curve will do something like this. Because if you're adding base, the pH should increase, right? What we are looking for are sharp, sharp changes in pH. Those happen around the equivalence point. Now, let me just look at what else I was saying here. Oh, nothing really important here. Okay. Now, again, if I'm adding sodium hydroxide, my end pH should be higher than what I start at. If I was adding HCl or some other acid, I would start at a high pH because there's no acid in there, and then I would react it with the base. As the base gets eaten up, the pH goes down. So our goal is to plot out all the different volumes of what can happen. And to do that, we're going to ask this question. What's in the beaker? When you do a pH titration question, what I want you to do is the following. I want you to draw, literally, a beaker. So, something like this. What's in your beaker? And when you are doing the question, so like let's say you're titrating HCl plus sodium hydroxide. And the products are who gives a shit. So this is your analyte. And it's what's in the beaker. This is your titrant. And it goes in the burette. What's in the beaker? Well, right now it's just HCl, right? You can clearly see that. So if I asked you to give me the pH before adding NaOH to it, you'd be like, oh yeah, I could totally do that. Whatever the molarity of this thing is, we'll just negative log it. That would be its pH, right? You'd be surprised at how many people will now get this question wrong. Because all I'm doing is saying, oh, we're titrating. And people would be like, I don't know how to do that. I'm like, yeah, you do. You totally know how to do that. You could tell me the pH of a 0.1 molar HCl solution. That's trivial. It's just 1, right? Minus log of 0.1 is 1. Be like, oh, well, we already did that. Yeah, now we're applying it. So you have to be really careful that you don't let all the stuff that we've covered already confuse you now that we're doing it with this new technique. So whenever you are given a problem and asked a specific question to find the pH at like some amount, tell me what's in the beaker. Sit down and draw it out. If I added some sodium hydroxide, what would end up happening is that these would cancel. And these would cancel. And then slowly but surely, I will have less and less and less and less of this in there, right? How about after I add so much that I go past the equivalence point? Well, now there's nothing else to react with, so I'm going to have these just floating around in here. And that's going to be my pH, however much hydroxide's in there. So think about what's in the beaker as we do these problems. For each problem, do a little sketch of a beaker, like literally draw it out. It will help you, believe it or not. Students really struggle with this part of the chapter because they don't sit and think about what's in the beaker. And that's my heartfelt, honest advice to you. Draw a beaker every time. And just what's in it. It will help you. Alright, so for strong acids and strong bases, this is just like what I showed you on the little picture of the beaker just a moment ago. Oops, I don't know why I didn't have my highlighter selected. That's weird. There we go. So if I have a strong acid reacting with a strong base in either orientation, i.e. the acid is the analyte or the base is the analyte, and I react it with the other thing in the in the burette, At first, when I add the titrant, it will completely neutralize analyte, but there's still more analyte left. So I will eat up my titrant and slowly consume the analyte. There will still be more analyte left in the beaker, though. But when I reach the end point, everything is neutralized. There is no titrant. There is no analyte. They have reacted with each other. Why are you doing this? My cat is licking my... He's licking my hand as I'm trying to write on the tablet here. What? What? No, don't lick the microphone. My goodness. When you get to the end point, everything is reacted. But you can keep titrating. You can keep adding titrant all you want. And so after the endpoint, you just have excess titrant. So how would you find the pH of these things? Well, here, in this first step, the pH would depend on what your analyte is, because it's what's in the beaker. Down here, I'm going to skip a step for a specific reason. After the endpoint, there's excess titrant, so the pH depends on the titrant. And in the middle here, at the endpoint, all the titrant and analyte are neutralized. Well, for a strong acid and a strong base, they completely neutralize, leaving only neutral species. So at the end point of a strong acid, strong base titration, the pH will always be 7. And so you can see that on our little graph. Where was our graph? There it is, right here. At the equivalence point, where all of the acid and the base is reacted, the pH is 7. Now, again, this is only true for a strong acid and a strong base, because the reaction of a strong acid with a strong base produces neutral products. And again, you know why that is, because we did the chapter, or the section in chapter 14.2. The conjugate of a strong acid or a strong base is neutral. All right. What happens if we do a weak acid with a strong base? We're going to do a strong acid with a weak base, and we'll get a different result here. But for any titration with a weak acid with a strong base, initially you have a weak acid, so your pH will depends on weak acid equilibrium. So if I had to ask you, what's the pH of your weak acid? Well, hey, you did a ton of those. I know this because I graded like 74 billion of them on the exam this week. So I know that you sort of know how to calculate the pH of a weak acid. That's trivial, right? Now, if you add some strong base to that to react with the weak acid, what do you make? Well, reacting weak acid with hydroxide would form a weak base. It's the conjugate. What happens when you have both of these in the solution? It's a buffer. Hey, we just talked about these. So when you add strong base to your solution, the pH will suddenly stop changing as quickly. And that's because you've created a buffer. So in the buffer region, you would just calculate the pH using the Henderson-Hasselbalch equation. Now, when you hit the end point, you only have the weak base left. So you'd calculate this pH. Just like you would treat it as if it were a weak base equilibrium problem. And then finally, at the end point, there's only a strong base left. So, since strong bases are easy to calculate the pH of, you just need to know the number of moles and the volume. You can figure out the molarity. You can figure out the pH. All right. So, we're going to be doing all sorts of crazy calculations on this to create a pH titration curve after the break. All right. I'm going to get more Fallout music going here. Hopefully no random outbursts from other windows that I have open of other music that I listen to, which is much happier than Fallout, but all right. So, oh, I don't have the timer up either. Let me do that real quick. There we go. No, I do not wish to update it. Stop asking me. All right. I'll start the timer. We'll start the music, and I'll see you in 10 minutes. Alright, we are back. What we're going to do now is we are going to create the pH titration curve of a strong acid and strong base. So our strong acid is going to be HCl. And our strong base is going to be sodium hydroxide. And so if I write the equation for this reaction, I just get a neutralization. Like, that's not anything super exciting, right? But what we do care about is that so this is my, let's see here. We have 25 milliliters of 0.1 molar HCl. So this is my analyte. And this is my titrant. Which means that my pH is going to start down here at the bottom. What is the pH of what's in the beaker? So first and foremost, this is what's in my flask. It's a strong acid. What would its pH be? Well, its concentration is 0.100. And if I hit log and then negate it, there's the pH. So the pH of the solution would be 1. That's easy enough to figure out, right? So that's why there's a 1 right there. So what's in the beaker? Just HCl. All right. What's the pH after I've added some titrant? Let's suppose that I added this much. We're going to add 5 milliliters of stuff to our titrant. 5 milliliters of NaOH. So what is the new pH? So what we had to do for the... Ooh, what did I just do? Oh, I just, like, killed everything. Oh, that's not what I want. Sorry, hold on. There we go. Okay. Sorry, I drug the... I drug the window or something and it, like, made a new window and then OBS didn't capture it. I was like, wait, why? Why is it gone? I forgot a decimal point. So add 5 milliliters of NaOH to 25 milliliters of 0.1 molar HCl. And I realize I forgot to write down the molarity. Is it? These are both 0.1, right? Yeah, okay. I'm just checking that. All right. So, what's in the beaker when we do this? Well, I had HCl, which was just this, right? And now I'm adding sodium hydroxides in here, so... But I'm only adding a little bit. So some of these are going to neutralize. I'm going to have mostly HCl's left, right? So let's see how that's going to shake out. HCl and NaOH. And we don't really care about these. Let's make a before-after table. And then what I'm going to do down here is I'm going to put volume, because that's going to matter in just a second. All right, before I did anything, how many moles of HCl are in there? Well, I have this volume and this concentration. So if I multiply molarity times volume times 0.025, volume in liters anyway, I will get moles. Before I added the sodium hydroxide, there was none in there, so I'm not going to have any volume for it. Oh, chill, I'll just do it like this. Then I'm going to add 5 milliliters of it. So how many moles make it in there? Well, that would be 0.100 times 0.005 And I'm going to subtract it from that, and I will add it to the products, but I don't really care about the products because they're pH neutral, right? So after I have this many moles of acid, and then this still gets used up, so there's none of it, right? But what's the volume of the solution? I had 25 milliliters, and I've added 5 to it. It's going to be 30 milliliters. Then I can figure out the concentration. This is going to be the part that people make a mistake on, is they forget, oh yeah, I added a volume. The volume changed, right? I'm effectively diluting it, but I'm also reacting, so it's not a dilution. But it follows the same principle. How many moles do you have over what volume? Well, I have this many moles of acid now. And this is the volume of the solution in the container. Wait a second, hold on. I should have a 0 in here somewhere. Why do I not have a 0? But I just typed in the wrong. Wait, no, that doesn't make any sense, though. What have I done wrong here? Hold on. 0.1 times 0.025 is that. Oh, I see my issue. Okay. Doing all the math right, but I just lost a 0 when I did this, so. There we go. Now I will get the number I expect to. Okay. So 0.0020. There we go. That's what I'm expecting. I was like, how could the concentration get bigger? Sorry about that. I made a math error when I multiplied two numbers together. That means that this must also do that too. There we go. So, just in case you were wondering what I messed up on, when I multiplied these two numbers together, I misplaced a 0. And then everything was 10 times too concentrated. And when I got down here, I was like, this number doesn't make any sense. It can't get more concentrated by reacting it. Okay. So this is the new molarity of HCl that's in the beaker at this time. And then if I figure out the pH of this, it'd just be So adding 5 mils of NaOH makes the pH go up to 1.17. And that makes sense because we're adding a base, so it should become a higher pH. And it's going to go very slowly because I have to react with all the acid before I can get the pH to hit the equivalence point at 7. So that should be our first result. So we get 1.18. Boop, we'll just put it on the graph there. So at volume 5, we have pH 1.18. So what I want you to do now is I want you to do that calculation for these volumes, 10, 15, and 20 milliliters, and tell me what volumes what pHs you get. So if I go back over here to this chart right here, you're going to calculate the number of moles of HCl and sodium hydroxide. So before, what's in the beaker? What change are we making? How much sodium hydroxide are you putting in there? What's thereafter? And then what's the volume? Okay, so go ahead and do that. I'm going to give you 5 minutes to tell me the pH of those 3 volumes. You can reuse the same table. Just cross out the old number, erase it, and add in the new number, and then keep going. I'll see you in a bit. All right, one more minute. We'll go over the answers. All right, so let's go over the pH for these two, or these three, actually, volumes. So I'm going to hit clear, and we're going to do this from scratch again. Well, if I had it clicked, we would. There we go. Ooh, almost knocked over my water. That would be bad. All right. So let's do sig figs, right? So 10 milliliters of 0.100 molar NaOH. That looks like HA. Hold on, HCl. There we go. So we've added 10 milliliters of 0.1 molar NaOH to 25 milliliters of 0.100 HCl. So if I were to draw my beaker here, there's my beaker. So I've got lots of H plus in here. And I've only added a few sodium hydroxide so far. So some of it will get canceled out. Some of the acid I have in there will be neutralized. But I still have predominantly acid in there. And we're going to see this as we write our expression here. So if I go before, change after. So HCl, NaOH, whatever. So before I have 10 mils, or I'm sorry, 25 mils of 0.1. So that would be 0.1 molar HCl times 0.025. So 0.025. I did it again. Look at that. I just don't write down all the zeros. So almost did the same mistake again. Not even tired today. I'm just clumsy. And then we'll do 10 milliliters, so 0.010 of 0.1. So this is my sodium hydroxide. So I didn't have anything before. So I'm going to react with this. I'll produce products, but we don't really care about the products, right? So this gets used up. Now I have this many moles left. And now what's the volume? Well, I added 10 milliliters to 25 milliliters, so now the volume is 40 milliliters. And the concentration of that would be... Oh, I typed in the wrong thing. There we go. 1.5 over 0.04000. So there's my new concentration. And I'm not exactly sure what I did, but when I typed 0, it made my pen all... Oh, I probably changed the hardness of the pen. There we go. There we go. So there's our concentration. And the pH would therefore be... 1.43. All right, so there was our pH at 10 milliliters. Let's do 15 milliliters. And so we're going to just change everything to red from everything I'm going to change, I'm going to turn red here. So 15 milliliters. So what happens here now? So this becomes 15. Because 15 mils times 0.1 mole per liter is 0.0015 moles. That would change this. So 25 minus 15 becomes 10. The volume changes. Because now I have 15 plus 25 is... Did I really make an addition error before? Oh, fuck. Okay. So it's 40 now. Previously it was 35. So this number right here... You know what? I can undo. So I could just do this. So undo, undo. So I found a mistake. How far back can I go? All right. Sorry, let's go back to this problem real quick. 25 plus 10 is not 40. 25 plus 10 is 35. So this is my concentration. And the pH of my solution here would be that. All right. There's that part. Now we can go to the 15 mil one. So that'll change. And that'll change. And this will change, because 25 minus 15 would be 10. And then the volume changes to 40. And then these change. So let's see here. So 0.0010 divided by 0.04. Is that, and then minus log of that is 1.60. All right, so that's 15. And then finally, let's do 20. Let's just get another color to indicate that we're doing something different here. So we got 20 milliliters now. So that changes the amount of base that's in here to this. 25 minus 20 would be 5, so I will reduce this down to 5. My volume increases. I have 45 milliliters total in here now, which means that the concentration changes. And gets really low. That's an eraser. And then what's the pH of that? We get that. All right. There you go. So calculating the pH of strong acids, as long as you don't mess up the volumes or do basic math errors like I've done so far, this is pretty trivial. It's the process that we're going to get stuck on, but we know how to calculate the pH of a strong acid or a strong base. It's just we got to figure out what the concentration was. And this is the part that's going to get people mixed up, because you want to put an accurate concentration in there. All right, so we'll add these to our graph. Boop, there we go. All right, next I want to find the pH at 25 milliliters. Now, At 25 milliliters, we would reach the equivalence point, because if I go back over here and I put in 25 milliliters here, let's go back to red, I guess. Then this happens, right? So I get 25 here. 25 minus 25 is 0. So there's my volume. And the concentration of HCl at this is just going to be 0. So what's the pH? Well, you can't negative log 0, right? You just get 0. Or actually, if you try and pH 0, you get negative infinity, which is not a number. So what is the concentration of this? Well, if it's neutral, then this concentration equals that from the autoionization of water, and the pH is just 7. So when everything completely neutralizes, you get pH 7. Of course, this is only true if you have a strong acid and a strong base. So if I go back to my little picture here and we look at what's in the beaker, I have added enough hydroxide here to cancel out all of my acids here. So all that's in here is just water. And so it's just the pH of neutral water, or 7. And so this is always true. The pH of the equivalence point is 7 if you are doing a strong acid, strong base titration. And that's the crucial part. They have to be strong acid, strong base, because if you have a weak anything, something changes, and we'll see that in the next example. Now, we can calculate the pH after 25 milliliters using the same process here. And so what we're going to do is we're going to go over here again. And now we'll change color again to indicate we're changing here. Let's do 30 milliliters. Now I have extra hydroxide in here, and it doesn't react. And you're going to see that in our table here. Now I have too much, right? I can't subtract 0.0030 from that. So at the end, right here, what I end up having is that there's no acid left. It's all gone. And that this is what's left over. And now my volume is 55 milliliters. And then down here, my concentration that I end up getting is not acid anymore, but is instead hydroxide that's left over. And so that would end up being 0.0005 over 0.055. So I have that as my pH. So if I log this, I get the pOH, and then I'll add it to 14. Or I'll subtract it from 14, sorry. And I get 11.96. There you go. So again, just track what your volume is. Do your before-after table. Figure out your concentration, and then you can figure out the pH. All right. And then you could keep doing this for higher pHs. We're going to I'm going to leave that exercise for you because I want to do the weak acid, weak base titration because I want to be done with chapter 14. Let's start something new on Wednesday. That'd be nice. All right, but this is what our titration curve looks like, and then we just connect the whole thing. Ta-da! Yes, I did draw that line. It is hard for me to draw on... I don't think I had a tablet when I made this line. All right. So by using what's in our beaker, we can figure out how to do the pH. The what's in the beaker will just give you an idea of, oh, okay, well, before here, I have too much acid. I did not neutralize it all with my base. After the endpoint, I have too much of the titrant. I have too much base in the solution. All the acid is gone, so my pH is going to look like my base. And then at the equivalence point, I've neutralized everything completely. Therefore, the pH would be 7. All right, there's our summary. So let's do... Okay, so here's strong acid being added to a strong base. So same thing. If I start with a strong base, I will have a very high pH. And as I add acid to it, the pH will go down. I hit the equivalence point at 7. And then it will decrease rapidly after that, down to whatever the pH of the acid is. All right. I'm going to leave this exercise for you, because we don't really have enough time to do it, unfortunately. Happy to go over this one in Discord. Let me know. You do this on your own and just show me your work, and we can go over the answers there. But I do want to talk about what happens when you have something weak in here. So for this example, we're going to do a weak acid titrating with a strong base. And we're going to titrate these two things. We're going to titrate formic acid with sodium hydroxide. Oops, I don't want to show that just yet. So let's go over here. I didn't mean to hit end on this. All right, so we'll just shove this over here in the corner. All right, so we're going to add sodium hydroxide to our formic acid. Let's assume like a really wide beaker. There we go. Oh, you know what I can do? I can just do this. What's in our beaker? Let's assume that we have not added any sodium hydroxide yet. So we would just have formic acid. So that'd be HCHO2. I'm just going to write down all these numbers here. Just so I have them on the screen, because now when I do this, we're going to just shove this out of the way. Okay. What is in the beaker? Specifically, we have formic acid, which is a weak acid. So if I wanted to find the initial pH, I would have to solve this as a weak acid problem. Weak acids are equilibrium problems, right? So we would treat this like a weak acid equilibrium. So I'd write out the weak acid plus water makes H3O plus and formate. And it's an equilibrium problem, so we make an ice table. Don't care about water. How much of this do I have? Well, I started with 0.100 moles per liter. I have essentially none of this. And I definitely have none of this. We'll react some. And produce some products. We should all be able to do a nice table by now. What's the next step? Well, if this is small, our math gets simplified to just this. And so that would be Ka was 1.8 times 10 to the minus 4. I don't know what I hit. 1.8. Unfortunately, I can't keystroke that. We're going to times that by 0.1. And we're going to square root that. And that's what x is. One, two zeros. Okay. All right, we got to check if x is small. 0.1 minus 0.004 would only change in this digit right here. So, should be good. So, if I type in this over 0.1 times 100, 4.2%. Yeah, so that check is fine. So that means that if this is x, which is right here, which is this, H3O plus, I can figure out the pH. I can also just get nothing, I guess. I don't know. There we go. For whatever reason, hitting the division key locked my layer, because of course it did. All right, so 0.0042 log minus. So there's our pH for just the weak acid. We're going to plot that on the graph. So there's our graph. All right. What is the pH after I add 5 milliliters of NaOH? So, what do we create when we do that? Hold on, let me put this back up here. Well, let's go back up to our beaker. If I add a strong base to my weak acid, I create sodium formate, right? Or just the formate ion is what we care about here. So what that means is that some of our formic acid is going to turn into formate, which is the conjugate of this. So what I have formed at this stage is a buffer. And so if I want to... Oops. So let's see here. So at 5 milliliters, we now have a buffer. So we'll use the Henderson-Hasselbalch equation. We just need to figure out... We'll go down here to solve that. We'll just scroll past everything. We need to figure out how much of what is in there. So we'll write out the expression here for the reaction of our hydroxide. With our formic acid. So before, change, after. All right. How many moles of formic acid are in there? Well, I have that written down. That's up here. So we got to scroll past all this again. So I had 25 milliliters of 0.1 molar. So 25 milliliters of 0.1 molar. How much sodium hydroxide did I add? I don't know what the concentration of sodium hydroxide is. I assume that it's 0.1 molar, but let me go check. .1 molar sodium hydroxide. Okay. So that's going to be 0.1 molarity times 0.005, because that's the volume I added. We didn't have anything to start. We had none of this, and we don't care about water. All right, I'm going to react with this one, but I'm going to produce this one. And that's going to be relevant because I'm making a buffer as I do this. So afterwards, I have this many moles of that. This gets completely consumed. And I have this many moles of that. Now, do I care about the volume here? I'm going to note the volume just real quick here. And I think I get one more sig fig, actually, from the previous number. But what we're going to see is that when I plug this into the Henderson-Hasselbalch equation, that it's not going to matter. So what was the Ka of this? This was 1.8 times 10 to the minus 4, right? So 1.8 times 10 to the minus 4. We're going to log that. We're going to negate it. So our pKa is 3.74 plus log of base over acid. So our base is going to be, so we'll enter its concentration. Whatever volume I enter in here is going to be the same as down here, and those are just going to cancel. So we don't really care about the volumes. So it's going to be log of 0.0005 divided by 0.0020. So let's do that. So plus 0.0005, 0.0020. We're going to log that. We're going to add that to pKa, and we get 3.14. All right, so that's the pH after we've added 5 milliliters of sodium hydroxide. We made a buffer, so we just threw all that info in the before-after table to create our buffer, threw it then into the Henderson-Hasselbalch equation. No problem. All right, so we'll add it to the graph. Boop. Now we can do the same thing again for volumes at 10, 15, 20. I'm going to do the 10 example over here just so we can see it again. So if I added 10 milliliters, we'll put it in purple here, this number would change, which means that we have less of this, and we have more of this. And then when I change those numbers, these numbers in the equation change too. So 10 and 15. And so now I would have 3.74 plus 0.0010 over 0.0015. Log of that added 3.74 is 3.56. So there you go. So that's the pH for 10 milliliters of base, which was then 0.0010 moles. So you should be able to calculate the molarity change, or not molarity, but the number of moles that changes as we add more volume. All right. Similarly, you can do this for 12.5, 15, and 20. Interestingly, at 12.5, the volume, or 12.5 milliliters, what you end up getting is the same amount of acid and base. So the log of that becomes 0. And then the pH is just the pKa. Then at 25 milliliters, what happens? At 25 milliliters, we have a weak base problem. I'm unfortunately out of time here. But I'm going to keep doing this whole thing so that we have it finished. And then we'll talk about the rest of the stuff for the chapter later. So I'm going to go over a little bit. I apologize here. So at 25 milliliters, what ends up happening? Hold on, I got to erase a bunch of stuff here. There, okay. So at 25 milliliters of sodium hydroxide, oh my goodness, why? Why are we not letting me draw? That's why, okay. So at 25 milliliters of sodium hydroxide, I have completely neutralized all of the formic acid. And this is all that's in the solution now. So at this point, this is all I have left, and this becomes a weak base problem. However, I've added this volume to the initial volume that was there. So the volume at this point is 50 milliliters. So we do need to note that. That's going to affect our results, right? Because we need to know the concentration of the weak base. Well, I had however many moles I started with of this, right? Which would be 0.1 times 0.025. So I have that many moles divided by 50 milliliters. I don't know why it gave me 0. Why are you like this, calculator? There we go. So the amount of formate that's in here has a concentration of that. And that makes sense, right? Because the initial concentration was 0.1. We dilated it to double its volume. So it's going to have half as much. And we've turned all of the formic acid into formate because we're at the end point. So now we can just do a weak base problem. So this will react with just the water in the solution. And we'll get hydroxide and formic acid. And we treat it as an equilibrium. Wow, that's not where I thought my cursor was. There we go. Now, this number comes from, again, the concentration and the volume that we have in there. So be careful because the volume is not the same as it was at the start. So we need to use this number. All right, this is a base, which means that the equilibrium constant will be Kb. And we're going to do the same assumption. X is small. We'll just assume it's small. We'll check it later. But that means that this expression will be 0.0500 times KB equals X. All of that in my square root. I need to figure out what KB is. I know that KW over KA will be KB, which is 1 times 10 to the minus 14, divided by 1.8 times 10 to the minus 4 was our Ka for formic acid. So let's type that in the calculator real quick. Divided by 1.8 times 10 to the minus 4. 5.6 times 10 to the minus 11. Yeah. So there's KB. That'll be right there. So X is going to be that number times 0.05, then square rooted. And we can tell that X is very small. And so X is just hydroxide because that's what's in our ice table. POH should be that. pH should be 14 minus it. Now it's a weak base, so our pH should be just over 7, right? So at the equivalence point, when there's only a weak base in there, you'll have a pH above 7. This is normal. In fact, all weak bases have pHs above 7. If they didn't, they wouldn't be pH, or they wouldn't be bases, right? They'd be acids. So all right, so we throw that on the table there. Okay, we already talked about that. Let's plot that on the map there. There we go. All right. Now, after the equivalence point, it ends up being just whatever titrant you're adding. So this is going to be the same problem we did with the strong base, strong acid. So I'm going to have 5 milliliters of hydroxide that is basically unreacted, however many moles that is, divided by the total volume. We can then figure out the pH, and we can just plot those on the graph, and then our curve is done. All right. So I want you to practice with these because there's really not much benefit in me just doing these examples over and over and over again because it's really the trick is just going to be what's in the beaker. Tell me what's in the beaker at each step. Find the pH by doing the type of problem that we've already done in this class. So at the start of the curve, what's in the beaker? Right here. What is in the beaker? It's a weak acid. Do an equilibrium table, right? Do an ice table. What's right here? This is a weak base. Do an ice table. What's in the middle here? This is a buffer. Do the HH equation. What's up here? Excess strong base. Just calculate the POH and then figure out the pH. So you know how to do all of these things. The trick is going to be just realizing what's in the beaker. Then what do you do to do the calculation? You could set up the before-after stoichiometry table to help you. If that helps you visualize better or draw a picture or just do something, right? All right. So when we come back on Wednesday, we're going to finish Chapter 14, thankfully. We'll talk about polyprotic acids. I'll talk about weak base, strong acid. It's just basically the opposite curve of this. You start at a high pH, you can go lower. Yeah, and then we'll start with Chapter 15, which is basically a solubility product, which is insoluble stuff, has an equilibrium constant, etc. So I do want to thank everybody for coming out to the lecture. I hope everybody on the campus is okay if you're watching this from your dorm. Please stay safe. Make sure that you follow all directions by EVCC personnel who are operating in your best interest to keep the campus secure. And if you have any questions about anything that we did today, make sure you ask it to me in the Discord. I realize that this is a very complex topic because it's more or less just review of everything that we've done. All right. We will finish Chapter 14 on Wednesday, so that's all I really have for today. I didn't hit this button. Let me try that again. That's all I really have for today. Thanks for sticking around. Ask me any questions you have in the Discord or by email. I will post exam number 1 scores tonight. See you on Wednesday. Take care.